Hello, Math 120, and I'd like to do some problems from homework assignment 3.2, which has to do with word problems, more specifically, word problems with two variables unknown. And that may sound like it's tougher, but in some ways, having two variables to play with makes it a little bit easier because sometimes it's easier actually to write our equations. Sometimes having to force a problem into one variable sometimes actually can make it harder. So let's start off with this first one. This first one is just basically taking a look at numbers in the English language and translating that into a system of equations. So once again, we've got two variables to play with, and that means in order to solve an equation with two variables, we're going to have two equations. That means two variables, two equations. All right, let's start off with number one. Number one, the first thing we probably should do is we should define our variables. And 95% of the time or more, the question at the end tells us the variables we need. It says find the numbers. Okay, well, we got a first number and then another number. So I'm just going to call that let x equal the first unknown number and then let y equal the second unknown number. So we could always go back and refer back and realize, okay, I just found x. Which one is that? Oh, that's the first number. Oh, I just found y. What is that? That's the second number. Now, when we go ahead and read this, let's go ahead and read the first line. It says the sum, oops, let's see, it needs to be a little bigger, I think. It says the sum of twice a first number. So the sum of twice the first number. So when it says the sum, we got to add. So it's the sum of twice the first number and 3 times another number. So it's going to be the sum of twice the first number, 2x, twice the first number, and the sum of that and 3 times another number, so it's 3 times the second number, y. So it's 2x plus 3y equals, and there it is, equaling 15. There's our first equation. The second equation looks like it's right here. Now we want the difference, that's subtraction. The difference of the numbers is 25. So the difference of the numbers is 25. Okay, so this can be done either by using substitution or by elimination. Either way is fine. I'm going to go ahead and do substitution. So I'll go ahead and solve for x. So what I will do is, let me show right here, and I think I'm going to use red so I kind of can show my substitution a little better. What I'm going to do is I'm going to add y to both sides. This gives me x equals y plus 25. Now, if x equals y plus 25, that means that I'd have to believe that if I put in y plus 25 for x on the other equation, remember we always have to use both equations, but if I do that, I'm going to still have a true statement which says 2 times x plus 3y equals 15. Now remember, we just found out that x is the same as what? Y plus 25. So what that substitution does for us ultimately is we get a new equation that's valid, 2y plus 50 plus 3y equals 15. A new equation that is valid, and that new equation only has y's in it, so that's really nice. So we're going to combine our like terms to make 5y plus 50 equals 15. Subtract 50 off of both sides, and 5y equals, what's that, negative 35. And finally divide by 5, I'm going to get y equals negative 7. Remember, y was my second number, so that's my second number. I need to get my first number, and I can just take that negative 7 and plug it in for y. Let me just use some color to kind of highlight that idea again. If y is the same as negative 7, that means I can replace my y with negative 7. So that's what I'm going to do. Take this guy right here and say x equals y, which is negative 7 plus 25. Once again, just to highlight my substitution. So now we have negative 7 plus 25, which is the same as 25 minus 7. So that gives us what, 18? And let's see, it says the two numbers are, okay, so my first number, remember my first number was x, so my first number is 18. And that second number, or they also called it the other number, is negative 7. So 18 and negative 7. And that's done. Number 2, talking about a fast food joint. Fast food joint. You go there, one patron goes there, buys 7 cheeseburgers and 3 medium shakes. Cost $17.01. Geez, 7 cheeseburgers, 17. Yeah, something's not right with the numbers there, right? In terms of time period. I mean, is this the 50s? I don't know. Anyways, at the same fast food joint, 2 cheeseburgers and 5 medium shakes cost $12.50. What is the cost of a cheeseburger? What is the cost of a medium shake? So there is the question again. And usually, like I said, it's like 95 or more percent of the time, that question tells you what your variable that you don't know has to be. So we're going to go ahead, and you could use x's and y's. That's the most common. Those are the most common variables to use. Some people like to use variables that kind of remind them of the word problem to help them remember what they're talking about. I guess we'll go ahead and do that. Let C equal the cost of one cheeseburger. I'm running out of space. One cheeseburger. And then let, I guess, S for shake equal the cost of one, is that what did it say, medium shake? Where's my problem? Medium shake. Okay, so I've got my 2 variables. Now, what we have here, let me use some color. What we have here is here's our first situation, 7 cheeseburgers, 3 medium shakes cost this. So really, we can write an equation for the cost of this, right? And we would say the cost of this first situation in red was $17.01. Well, what do we have here? Well, we had 7 cheeseburgers. What's the cost of 7 cheeseburgers? Well, if a cheeseburger was $1, then it would be 7 times $1. We don't know what the cost of a cheeseburger is. That's why we have C is the variable for the cost of one cheeseburger. So if I have 7 of those and I multiply it by the cost of one of them, that tells me the cost for all those 7 cheeseburgers. Similar logic is I've got, 3 shakes here, 3 medium shakes. I don't know the cost of a medium shake, so that's why we're using this S. And so 3 times the cost of the medium shake, which is S, is going to give me the total cost of the shakes. So the total cost of the cheeseburgers plus the shakes gives me the $17.01. And there we go. So a similar logic, similar line of logic is reading the next line, which had at the same place, we got 2 cheeseburgers and 5 medium shakes cost $12.40. So that would be 2 cheeseburgers plus 5 medium shakes, and that's a cost of $12.40. So we just made 2 equations of the cost of those meals. Now, you can do this by substitution or by elimination. I'm going to go ahead and do elimination just to show different ways of doing these things. Remember, we've got solving equation or graphing equations, which is not the best for accuracy, right? Because it's hard. If the intersection point was $3.25, it's so hard to see on a graph. Although it's good for conceptually what's going on. Substitution is great, gives us a real accurate answer. It's a algebraic technique. And addition elimination, which I'm going to do right here, is also great too. So addition elimination means you have to figure out what you got to either eliminate your C's or your S's. And either one would be fine, really. But I'm going to go ahead and eliminate my C's right here. So let me just have a little note. If you want to get rid of your C's, what is the least common multiple for a 7 and 2? That means a number that 2 and 7 go into. And the smallest of those numbers is 14. So that's kind of like your target number if you want to eliminate the C's. So let's do that. Now one is going to have to be positive 14 and the other one's negative 14. And it doesn't matter which way you go with that. So I'm just going to say negative 2. And then this one gets multiplied by positive 7. And that'll give me opposite 14 and positive 14. Negative 14 and positive 14. So remember, you also have to multiply the right-hand side by that same quantity. And same thing with this right-hand side by 7. And then now we can just go ahead and simplify the problem by distributing a negative 2, which gives me negative 14c. And distribute a negative 2 times 3 is negative 6s. And that is negative 2 times 17.01 gives me negative $34.02. Let's do the next line, which is multiplying by a 7. So 7 times 2c is 14c. And notice we've got opposite. That's exactly what we need. And then we've got 7 times 5s right here. 7 times 5s, which gives me a plus 35s. And then we've got 7 times $12.40, which is $86.80. Now, because these are opposite, we're ready to add them up and get 0c. That's the elimination step. We've got 35s and a negative 6s, which makes what? 29s. And then we've got negative $34.02, and then plus a positive $86.80. This becomes $52.78. Divide by 29 because we want to solve for s. And we get $1.82. So we just found out, have more space? Good. We just found out that the cost of a medium shake cost $1.82. Okay, now I need to figure out what the cost of the cheeseburger is. So let me get some color here. So if you believe, well, let me copy one of these equations down. I'm just going to copy. You can take either equation at this step, by the way, but I'm going to take this one right here. Whoops, I just erased stuff. I'm going to take this particular equation, the second one. I'm going to write it down. A 2c plus 5s equals 1240. Okay, now if you believe that that s is the same as $1.82, which you should because you did all that work, or we did the work, or I did the work, then you can replace s with, you got it, $1.82. So this is going to be 2c plus 5 times s, right, which we know the value of s now is $1.82, equals 1240. So now we go ahead and multiply $5. So we got 2c, and we've got 5 times $1.82 gives me $9.10. Yeah, I'm going to double check that real fast before, so we've got 5 times $1.82 gives us $9.10. Okay, and then that equals 1240. We subtract 9/10 on both sides. 9/10 on both sides. We get 2c equals $3.30. We go ahead and divide by 2, and we get c equals $1.65. So that was a little hard to believe. Milkshakes are $1.82, and a cheeseburger is only $1.65. Okay, so cheeseburger cost $1.65. This is definitely not at the movie theater. No way. So there it is right there. Let's move on to the next one. The next problem is a mixture problem. And mixture problem with coffee is a little different flavor than a mixture problem with liquids or we have one coming up at the very end, which is a mixture of alloys, which is a metal mixture. Then we have mixtures of alcohol or acid, different things like this. This is a mixture of coffee, which is something I love, the coffee at least. But I think what I want to do is I want to see. I think I gave some extra space. Yeah, extra space just to kind of get this idea down. Okay, so let's start off by just talking about this. If I had a canister of coffee, right, and I told you this is, I don't know, it's just gonna be some coffee that cost. Oops, I lost my pen. That cost $3.50 per pound. Okay, and so that's the cost per pound. And then down below, I always write the actual how many pounds are in that container, right? And this kind of thing you can see. You go to the store to buy coffee in bags, or this is like the old-fashioned can, but now they're usually in these expensive bags that, if you want Starbucks or Pete's or whatever. But anyhow, if you want to know the cost of that coffee, well, it's $3.50 for every pound. And how many pounds you got there? 10 pounds. So when you multiply that up, what's the cost of that canister of coffee? Well, it's going to be $35, right? Just move the decimal over one because you're multiplying by 10. So it's $35 for that canister. Now, what about, I actually was aware of this stuff for the first time by watching, I think it was Bucket List. This Jack Nicholson was the super rich guy. And he wanted this cat, I think that was on his bucket list, cat crap coffee. And my sister-in-law and brother-in-law went to, I think it was India or something, and they got me some of this stuff because I'm a coffee lover, but I'm not sure about this cat stuff. Anyways, this is really expensive coffee. These cats go out and collect these little coffee beans just at the right time and chew them up, and their digestive enzymes do wonders for the bean, and then they leave it and go to the bathroom somewhere, and these people come and pick it up and sell it to people, dumb people like us that buy it for a lot. Anyways, this cost of this coffee could run $100 to $600 a pound. I got a little bit of it, and I didn't really see how great it was. But anyways, let's talk about cat crab coffee, which is if you get the good stuff, $600, which I don't know how you could tell, but $600 per pound. And let's say we had 10 pounds of this stuff. So what I'm trying to get you to realize is, you've got a couple things going on here. You've got the cost per pound, then you have the actual pounds, and then you have, well, what is the value of that whole canister? And that value is really important to get. How do you find the value of that whole canister? Well, it's $600 per pound. And how many pounds do you have? You have 10 pounds of this cat crab coffee. And so you are, I would say, a fool carrying around $6,000 worth of this stuff. Yikes. Anyhow, hopefully there's no kitty litter mixed in with it. But let's go ahead and take a look at the next. Sorry. And let's take a look at, I'm losing my train of thought thinking about this stuff. I mean, I want a latte right now, but the cat stuff, no. So let's see. What's the question here? I got to get focused. It says the coffee counter charges $7 per pound for the Kenya French roast. So I like to make these silly little canisters for some reason. I just always do it. And I've been doing it for probably 25 years or more. But anyhow, that's pretty sad, isn't it? So you've got these different canisters, and I always write it in this way because it helps us to see. Now they're talking about this Kenyan coffee, and they're saying the Kenyan, if I go back up here, the Kenyan, the coffee can, so $7 per pound for this Kenya coffee. So this stuff has a rate of $7 per pound. And then we got this Sumatran coffee, which I believe it said $6 per pound. So that's the rate for the cost of that coffee. Yeah. And then here's sort of the kicker. How much of each type can you mix together? So you got to mix them together and shake them around to make 20 pounds, to make a total of 20 pounds. So there's a clue right there. Our result when we add them together, they need to be 20 pounds. I could put a constant right there. And it also needs to sell for $6.50 a pound. It's got to sell for $6.50 per pound. Now, some people that are really kind of good at seeing what's kind of going on in a fast way, but may not be able to always formalize it. They may see that $6.50 is directly in between $7 and $6. So this problem is a little bit of a is a little bit too easy in the way that it's just going to be 10 pounds of one and 10 pounds of the other, because you see when you mix it together, when you have 7 pounds and 6 pounds and you want it to be dead in the middle of it all, well, that just means you just need an average of the two. You just need equal amounts of both. But let's not worry about that because they're not always that easy. So we have to have a real process to do this. So really what you want to do now is you want to go back to the problem. And remember, the question usually is what your variable is. And it says the coffee counter should mix blank pounds of coffee, Kenyan coffee roast, and blank pounds of Sumatra. So we're looking for, here's our X. And where can I sneak this in so I can work below this all? I think I could put it right here. I guess I'll sneak it in right here. It says let X equal the amount that's in pounds of what? The Kenyan coffee. And let's let, and like I said, you could use X, Y. Sometimes students really like it when you use a variable. I'm just going to use K for Kenyan coffee. But you got to know what it is. It's not the price per pound for the Kenyan coffee. It's the amount in pounds of the Kenyan coffee. So you got to be real clear with that. Let S equal the amount, not the price per pound, the amount measured in pounds of the Sumatran coffee. So those are our variables right there, right? So, if I was going to get some color here, K is the number of pounds for my Kenyan coffee, and S is the number of pounds for my Sumatran coffee. So that's just going to be a K there, and these are pounds, right? We don't know what it is, but they're pounds, and S, and these are pounds. So now remember up here where I did my cat crab coffee and this other unknown coffee. What could be worse than the second one? But anyways, to get the total price of that coffee, you have to multiply the amount times its rate, right? Price per pound. So we're going to do the same thing here. If I want to know how much this Kenyan pot of coffee costs, it's going to be $7 a pound times K. And if I want to know how much the Sumatra pot of, it's not a pot of coffee like it's already brewed, but it's the beans. How much the can of beans cost? Well, it's going to be $6 per pound. And how many pounds you have? I got S pounds. I know that abstract, calling it S pounds is a little bit hard, but that's algebra for you. So now we've got, the result, what we need is we need $6.50 per pound. And how many pounds do we have? 20. That's what they gave us. So when I multiply that little bit together, 650 plus 20, and we get what? 130, I believe. Yeah, 130. So that is the harder equation to figure out. Remember that when you have two variables, you need to have two equations so you can solve it by either what? Elimination, addition, or by substitution. Well, the second equation is actually really quite easy because the second equation is just talking about total pounds. And if you're just talking about total pounds, wouldn't it just be the pounds from this guy plus the pounds from this one better equal total pounds? What's total pounds? 20 pounds. So that equation is going to be pretty easy. Okay, what's the pounds of the Kenyan coffee? I don't know. It's K. What's the pounds of the Sumatra coffee? I don't know. It's just S. Right? That's the variable we defined back over here. So now we can do this by substitution or addition, elimination. I really don't care. I think I'm going to do it by using addition elimination. I see that I can multiply. If I want to eliminate the s's, that's already positive 6s. If I multiply this by negative 6, my new equation, so let's see if I can show my new equation right here. My new equation is going to be distribute the negative 6. That's going to be negative 6k minus distribute the negative 6 minus 6s. And we've got negative 6 times 20, which is negative 120. Okay, so now I want to copy, what can I copy? Just a slight color. I just want to copy this because this one's already in good shape. So I'm going to copy this one just right here above it, just so you can see what I'm doing. So I'm just going to copy that down. That's 7k plus 6s equals 130 rather. Now, see what happens? The elimination step is very productive because right here I've got a positive 6s, negative 6s, s's are gone. And then this is kind of nice too because I've got 7k minus 6k, which just gives me 1k. And then that gives me the answer over here, 130 and a negative 120, well that's 10. I just figured out I need 10 pounds of this Kenyan coffee. And of course you can always just go back to either one of these original equations, and of course the easiest one is this one right here, before I multiplied it by 6, by the way, negative 6. So I'm going to take that easy equation that just says the number of the pounds of Kenyan coffee plus the pounds of the Sumatra coffee better equal 20. And so therefore, if we take a look and we say, well, if k equals 10, then I can replace that k with 10. So I replace the k with 10. Of course, you know what to do now. Subtract 10 on both sides, which just gives me s equals 10. So what do we just figure out? I guess I should put that box around that because the box is my answer. We could answer this in a basic statement. I don't need to have it too crazy. Well, you're doing it online, so you're just typing it into their little fill in the blanks. But basically, what you're going to need to create a new kind of coffee that mixes Kenya plus Sumatra, and it costs $6.50, and you got 20 pounds of it. What do you need to do that? Well, you're gonna need 10 pounds of what? Of the Kenyan coffee. And you're also going to need to mix that with 10 pounds of the Sumatran coffee. Okay, all right. So next, number 4. Number 4. So just to let you know, this mixture problem kind of thing is a classic kind of problem. So I wanted that to be in here, and it comes up again in math in the future, or pre-calculus, calculus, stuff like that. They just use different techniques usually. But there's a mixture problem. And here's another classic problem, which is linear motion, rate times time equals distance. But we're going to do this with an airplane that flies into the wind and then flies against the wind and with the wind. And so that's sort of the trick to kind of figure that piece out. And then the other thing is, another similar question to this is a boat going down the river and up the river, so those two problems in my mind are the same kind of problems. You want to try to group those together. Here's the first attempt at this. Ooh, I just zoomed into nothing there, into a speck, I guess. But it says the airspeed of a plane is the speed through the air. The ground speed of a plane is the speed relative to the ground. The ground speed of an airplane is affected by the speed of the wind. So we're really looking for the ground speed. I'm sorry, we're looking for the airspeed. See, the ground speed of an airplane is affected by the speed of the wind. The airspeed of the plane is blah. So essentially what we're doing is we're looking for how fast can, and often authors will write it this way instead of calling it ground speed, airspeed. But they'll say, we're looking for the speed of the airplane in still air. So there's just no confusion. Because remember, if you're flying an airplane and the wind is behind you, pushing you, there's two rates going on, right? There's the speed that the airplane could generate with its little propellers, plus the wind blowing it, right? So that's where it gets a little bit confusing. So most authors would say something like the airplane speed. So they would say speed in still air, just so we know it's without the effects of the wind. Okay, so that's what we're looking for. I'm going to go ahead and draw a picture because I think for me, that's always the way to go, especially when I'm teaching. So it says that the ground speed of the air, blah, blah, blah. Okay, where did it go? So suppose, here it is right here. So suppose, that's not what I wanted. Suppose that a plane is flying 1,800 miles or 1,800 miles for 12 hours. So they're flying west. So let's just make this thing kind of make sense. So they're flying west. That must mean they're going this way. I didn't want that to be that color. So they're going west. It's that way. Let's call that west. So how far they go? 1,800 or 1,800 miles. I'm just going to sort of use different colors for different things. Remember the important formula here is that rate times time equals distance. So that is the basic formula for all of these kind of problems that we're doing in terms of when you have a rate, a velocity, a rate, and distance, and then time. So this person is able to, the plane flies 1,800 miles west and requires 12 hours to do this. So I think I put my time in green, 12 hours. And flying 18 miles east, so then we turn around and they're going east. Of course, the distance is still the same. And now the time changes. So why is the time changing? It takes 9 hours. Well, the time is changing because, I'm trying to do rate in red, by the way. The time is changing because we have something that's changing everything. There's wind. There's wind that's blowing in that direction towards the east. Right? We're going to call this W as our speed for wind. Now you can see what's going on, right? The plane has the same exact rate going both ways. Let's see, find the airspeed of the plane and the effects of the wind resistance it has on the plane. So the plane is going the same speed in both directions, but it only takes 9 hours going this way because the wind is helping it, and it takes 12 hours. It slows down because the wind is hurting it, right? Because the wind is blowing against its progress. So really the key to understanding this problem is to realize that the airplane speed has two speeds working together or against each other. So if you're going with the wind, right? So you see they're going this direction, which is with the wind. Well, that means it's going to be the airplane's speed plus the wind speed. Okay, and we probably should do a let statement over here. Let W equal the speed of the wind, and then let A equal the speed of the plane. Got to be careful because the actual plane has two things going on. It's for the speed of the plane in still air, where the wind is not helping or hurting it. So that's the actual speed. So when we're going with the wind, it's the airplane speed in still air plus the wind speed, which gives its overall speed. When we're going the opposite direction of the wind is hurting us. So it's going to be the airplane speed and then minus the wind speed. Take away the wind speed. Okay, and so Now what I like to do, I got a picture going. That's one of the strategies for word problems. Another strategy is to make a chart to organize your data. So I'm going to do that. I'm going to make this little chart here. And let's see. Yeah, the first one is going to be westbound. But maybe even better yet is to call it westbound is when we're going against the wind, which is a great song, by the way. And then when you're going eastbound, you're going with the wind. Okay, so now remember that all important formula, and I'm going to try to get my colors to match up. I used what? Red for rate, and I believe I used green for time. Okay, so rate times time equals what? Distance. This just helps to organize all the little pieces that are in this problem. So now when we're going on the westbound journey that's going against the wind, what's the rate? Well, the rate is in red right here, and it's going to be the airplane speed minus the wind because we're going against the wind. How long did it take them? It took them 12 hours. Pretty long. How far they go? They went a distance of 1,800 miles. Now, what happens when they go with the wind? The wind is helping them. So, what's the rate? I don't know what the rate is. I did define it up here, right? Let W be the speed of the wind and let A be the speed of the airplane in still air. So, going back home or whatever, going eastbound, it's the speed of the airplane in still air plus the help from the wind plus W. How long did it take them? It only took them 9 hours. That makes sense because they had the wind pushing them, making them go faster. How far they go? Well, in this case, they went the same distance. And now we have our equations that we can solve. Because remember, rate times time equals distance. There's two equations there. Let's take a look at this first one right here. And it's going to be rate times time. I'm going to do time first. So you could change the multiplication direction. I'm just going to do time because of distribution. It makes more sense to write it this way. It doesn't matter though. So it's rate times time or times rate equals a distance of 1,800. Let's see. I want to move this over. Let's see. Yeah, I want to save some space real quick so I can work the problem horizontally for a little bit. So once again, I'm looking at this line right here going against the wind. Okay, it takes 12 hours. And so rate times time equals distance of 1,800. And what was the rate again? Well, the rate going against the wind was the airplane speed in still air minus the wind speed. And then we've got the other situation, which is this guy right here, right? So the time is 9 times the rate, which happened to be, now we're going with the wind, so it's going to be airplane speed in still air plus the wind. And that gets multiplied, rate times time equals the distance of 1,800. There's our system of equations right there. Now, what you could do, I meant to have even more space, and I just see another thing. But what you could do is distribute the 12, distribute your 9. That's a normal thing to do. Numbers get a bit big. Here's an alternative that is when you see this, you're going to want to remember this. But if 12, because this is 12 times, right? So how do you undo multiplication, division? Well, if this number over here is divisible by 12, you're going to simplify your problem quite a bit. 12 divided by 12 gives us 1, and if you distribute 1, you're just left with A minus W equals, and then what is 1,800 divided by 12? Well, it's a nice whole number of 150. If it's not a whole number, it just gets to be, you get decimals, and it gets to be a pain, but you still can do it. And then look at this one. Same thing. If I divide by 9 now, is 1800 divisible by 9? And yes, of course it is. So when we do this division, we simplify our problem to a plus w, because remember, this is 9 over 9, which is 1. If you distribute 1, you just get a plus w. And on the right-hand side, of course, this is just going to equal 200. 1,800 divided by 9 is 200. So the beauty of doing this is now, check it out. These guys are already opposites. So the addition elimination method is just all ready to go. And the numbers are so easy because right here we have a plus a, which is 2a. And that zeroes out. And we're left with 200 plus 150, which is 350. And then we simply just solve for a, divide by 2. And a equals 350 divided by 2 is 175. We just figured out the airplane speed in still air. And we can figure out what the wind is by grabbing this nice and easy simplified equation, which says airspeed plus wind speed equals 200. And or airplane in still air. So a plus w equals 200. Let's just keep it that way. And so if I put, in, substitute 175 for a, subtract 175 off of both sides, we get w equals 25. I think we figured it out. What's the answer? Plane speed. It's a plane's speed, and that's in still air, is 175 miles per hour. And then the wind speed, I had a colleague that said a student wrote down on the answer, wind speed in still air. Well, wind speed in still air, that's 0. Well, no, so wind speed is actually, in this case, 25 miles per hour. And there we go, got it. Check, check, check. Let's look at the next one. Janice is thinking of 2 numbers. So back to, this falls in the category of number sense problems, turning numbers into systems of equations. So let's see here. Janice is thinking of 2 numbers. So this is where we're just going to let x equal the first unknown number, and then let's let y equal the second unknown number. Okay, let's see if we could do this. The first problem, the first bit of information says Jan's thinking of 2 numbers. She says that 2 times the first number plus the second number. So there it is right there. Let's see. 2 times the first number is x, so 2 times x, 2 times the first number, plus the second number is y, is 58. Well, there's our first equation. Let's see our next equation. It says the first number plus 3 times the second number is 64. So the first number, x, plus 3 times the second number, 3 times y, is 64. All right, so we can use substitution or we can use addition and elimination. It's totally up to you. Substitution wouldn't be too bad because you can solve for x, right? And just stick it in there. Let's just go ahead and do that since it's because I'm just trying to give you variety, substitution or addition elimination. Let's do substitution. So what I'm going to do is I'll do this in red, and I'm going to subtract 3y. Why? Because I'm going to try to solve for x. This says now x equals 64 minus 3y. So if you believe that x equals 64 minus 3y, then you can now remember you have to sub it into the other equation. We started with this one. You have to sub it into the other equation for x, which is right there. So now we're going to get, I'm going to copy this equation down with my new substitution. It's going to be 2 times x plus y equals 58. Now remember, we just said that x, we know now x is just 64 minus 3y. So we could do that substitution. And once again, the key thing that happens with substitution or addition elimination is you have a new equation, and this new equation, what? It only has one variable. In this case, it only has y's. So 2 times 64 is 128. 2 times negative 3 is minus 6y. And then we have plus y, and we have equals 58. So let's go ahead and combine like terms of 1y. Whoops, let's do it like this. So now we have 128 minus 5y equals 58. Subtract 128 from both sides. And we get negative 5y equals a negative 70. Divided by negative 5. And we get y equals, what does y equal? 14. Negative makes a positive 14. Okay, and now you got that 14. You could just simply sneak that 14 back into this equation and solve for x. So x equals 64 minus 3 times, what do we find out y to be? Well, we just found out that y is 14. So we put 14 in for y, and we solve. So now we know that, oh, did I put it in a different one last time? It doesn't matter which one I put it in. Yeah, anyhow, so let's go ahead and solve. And 3 times 14 is going to be, 42, so it's negative. So we've got x equals 64 minus 3 times 14, which is 42. And 64 minus 42 gives me 22. Okay, so we figured it out. The first number. First number is, x was our first number, so 22. And our second number is 14. Okay, let's keep it going. Oh, back to the coffee. All right. So this is very similar to the last problem. The good thing is it doesn't have that quality where it puts it right in the middle where it's going to be exactly 10 of one and 10 of the other. But the problem is very similar. So let's see if we can do it now. We already talked about this once, so let's see if we can get our nice little visual going here. We've got the Kenyan coffee plus the Sumatran coffee. And that's going to equal my total coffee. They want a new mix. Okay, so they got the Kenyan coffee, which costs $7 per pound. Sumatran coffee, which is a little cheaper, $6 per pound. They're going to tell us that, what do they want? They want us to, how much of each type to make. They want to make 20 pounds, okay, 20 pounds. They want 20 pounds blended that sells for, there it is right there, $6.35 per pound. So this has to be 20 pounds, and it has to be exactly selling at $6.35 per pound. And I touch this again, and there we go. Hopefully that looks like a 3, $6.35. Let me touch it one more time and ruin it more. There it is. Jeez, okay. One more time. Okay, $6.35. So now we don't know how many pounds it's going to be needed for the Kenyan coffee. So I'm going to say let K equal the amount. This is going to be amount measured in pounds of what? The Kenyan coffee. And then let S equal the amount that's measured in pounds of the Sumatran coffee. So you do want to put that down because, like I said before, it can be confusing. Like, what is K standing for? Is it standing for the price per pound of the Kenyan coffee, the total amount of pounds of the Kenyan coffee, the total value of that one canister? No, it's just the pounds, the amount in pounds of the Kenyan coffee that's needed to make this blend. So this actually is just going to be K here, and S here is the amount. And remember, how do we actually figure out how much this is valued at? I see I'm going to run out of space pretty quick here, so I got to start conserving a bit. In fact, let me zoom. Well, I can't zoom in too much, but let me zoom in a bit. Try to use a smaller font size or pen tip rather. So it's going to be so it's how much does this container cost? Well, it's $7, and then it's times the amount of pounds, and it's K pounds. And then the next one is $6, and how many pounds of that do you have? S. And then the next one is going to be 20 pounds times 6. So when we multiply these together, so let me write it down. So $6.35 times 20 pounds. And what does that make? That's going to make 175 or 127. So that's what that is, 127. So there's the beginning of our system of equations. Probably don't need that multiplication dot there. That just might confuse it a little more. And then what's the easy equation? The easy equation is the number of pounds in the Kenyan pot is K plus the number of pounds in the Sumatran pot is S, and it better equal total after we blend it, which is 20. Just like when we did before, I think this is going to be very easy if we just multiply the second equation using what do we call it? Addition, subtraction, or addition, elimination rather. I want to eliminate the s's, so I'm going to multiply the bottom equation, the left and right, by -6. And in doing that, so let me just copy this one down right here. So I'm trying to zoom in to give ourselves a little more space. And remember, when I copy that back, it's just 7k plus 6s. 7k plus 6s equals 127. And when I make this multiplication, right, I've got to distribute -6. So that makes -6k minus 6s. And then 20 times the -6 gives us that -20, -120. Now when we add them up, some beautiful things happen, of course. The s cancels out because 6s -6s. And then 7k minus 6k gives me just 1k. And on the right-hand side of the equal sign, we get 7. So we just figured out that that k equals 7. So the next thing we want to do is maybe go to this simple equation that we had at the beginning, which said k plus s equals 20. Well, we know that k is 7. So we are going to replace k with 7. So now we've got 7 plus s equals 20. And if we subtract 7 from both sides, we get 13 rather. Okay, so what is going to be needed to make this new blend of coffee? We're going to need 7 pounds of the Kenyan coffee, and we're going to need 13 pounds of the Sumatran coffee. That'll give us a new blend that has a total of 20 pounds that has a price of $6.35. All right, so now we've done the mixture problem with coffee twice. Hopefully that's starting to come together a little bit. Jonathan and Samantha row their canoe. Okay, now, once you put this in your head, this is going to be the same kind of problem as flying your airplane with the wind and against the wind. Okay, it's the same kind of problem. How much space do I have? I don't have as much space. I got to be conserve a little bit here. So let me zoom in. And when I read the problem, it says that this person is going, maybe I better read the problem. Jonathan and Samantha row their canoe 36 miles downstream in 3 hours. Sounds like is Is this a date? I don't know. Let's see. After a picnic, yeah, after their picnic, they row back upstream. Okay, let's see what's going on so far. So we're going. Let's call this downstream. Let's see how we do with space. I don't like that thin pen when I'm zoomed out. So they're going downstream. Well, which way does water flow? Downstream. So I actually like to call this with the current, because that's kind of specific. It helps us kind of see things, I think, a little bit. So they went 36 miles. I'm doing the miles. I'm going to use my same color coordination before. Miles will be in black. 36 miles in 3 hours. Hours will be in green. Then what happened? They started rowing back upstream. Now, upstream is against the current, and we know that that is always going to be harder. So now they're going upstream. And some bad things start to happen, I think. After 4 hours, they only travel 6 miles. Uh-oh. So after 4 hours, remember time is green, so after 4 hours, they only traveled 8 miles. That's when you start kind of worrying. And I don't know if they had a glass of wine, but that starts wearing off too, and trouble, right? They've gone 4 hours. They did an hour more of rowing than when they went on their little happy picnic. They've been rowing an hour extra on the way back. They've only gone 8 miles, and then they got to go total 36 miles. This is sounding like this is going to end poorly to me. But anyways, assuming that they canoe at a constant rate and the river's current is constant, find the speed at which Jonathan and Samantha can row in still water. So even though we're just trying to find the speed that they can row in still water, there's still that other lurking variable out there, isn't there? And that other lurking variable is the speed of the current. I'm going to draw in red, because red is going to be my current or my speeds. And I'm going to put right here, this line right here, which is going to be, I'll call it R for the river's current. So speed of the river. And just by this scenario, it sounds like this river is pretty fast compared to how fast they're going, because they're not going very far in 4 hours. So now the thing that we're missing here is that critical piece. When you're going with the current, we can measure, let's say, your boat speed plus the river current speed. So you're happy because you're getting a lot of help. But when you're coming back home against the current, it's gonna, what's your rate going to be? It's going to be the boat speed minus the current, the river speed, which is killing you right now, and it's going to make you go much slower. So those are the pieces. Let's go ahead and see if I can squeeze in my chart on the right hand side over here. So this is going to be downstream. And I also like to think of this as, like I said before, downstream is going to go with the current. And then this is upstream, which is against the current. Now remember, we have rate times time equals distance. I'm going to use my colors. Rate is in red. We didn't define our variables, darn it. That's got to happen right now. So I'm going to say let B equal the boat speed in still water. Or I guess the canoe, but I'm going to call it boat. Boat speed that's in still water. That means How fast can you row that canoe or boat without any current? I guess in a swimming pool, right? So how fast can you actually generate without any current helping or hurting you? And we're going to let what I use, R, equal the river's current or the river speed or speed of the river, also called the current, right? So if I want to figure out what is the rate when I'm going against the current, well, it's going to be this guy right here. Sorry. What's the rate going downstream, going with the current? It's going to be right here. Going downstream with the current, you have the boat speed plus the river help. How about when you're going, okay, well, let's complete this. Then the next thing that we have here is it took 3 hours, so it's 3 hours, and that's the time. And then finally we have our distance right here. And the distance I can see when I was going downstream is 36. Well, then we've got ourselves coming back home. We just had lunch, we're all happy and full and a little bit sleepy, and now you got to really work your you-know-what off to get back home. It's going to be the boat speed minus the river's speed because you're going against the current. And how long are you rowing for? You're only rowing for 4 hours, but the shocker is you've only gone 8 miles. You're screwed. So now what we want to do is we want to go ahead and write our equation. And let's write it over here. I'm going to start running out of space. But remember, let's take the first guy right here, this first one right here, which is going to be 3. And I'm just using my color action here, times the rate, which is B plus R. And how far did we go for on this one, on this first journey? 36 miles. And then how about the second guy? Let's get our second equation. A second equation, they went for 4 hours. And of course, in this case, they're going against the current, so it's boat speed minus the river's current. And how far did they go? Not very far. They only went 8 miles. So this is the actual system of equations. Now you can distribute 3 and distribute 4, and that works just fine. But something, like I said on last problem, that's nice to notice is that if I realize that this is multiplication, right? So if I divide by 3 on both sides of the equation, I end up getting something really nice, which is the 3's cancel out, which is 1. Distribute 1, which doesn't affect that. So now it's B plus R equals, and 36 divided by 3 will give me 12, right? 36 divided by 33 divided by 3 is 11, so 12. Right, so we're good there. And then same thing here. And this only works if this number is divisible by, 4 in this case, and it is. So what ends up happening, is 4 reduces down to 1, and we end up getting this nice equation, B minus R equals 8 divided by 4 is 2. Man, how easy is this going to be to use the addition elimination with? Well, the r's are opposite, so they become 0. And b plus b gives me 2b. And 12 plus 2 is 14. And I divide by 2, and I get b equals 7. I just got the boat speed. Wait, what do they want? The speed at which Jonathan and Samantha can row in the water is 7 miles per hour. Well, I'm kind of curious. Now, we're done with the problem, by the way. But I'm kind of curious because, why is it taking so long to get back? How fast is that river actually flying along? So why don't we take this equation right here, which said B plus R equals 12, and I'm going to put in, well, if B equals 7, can I replace this with 7? And the answer is yes, you can. 7 plus R equals 12, and I subtract 7 off of both sides, and I get R equals, what is that? 12 minus 7, that's going to be 5. Well, there's your problem right there. Genius, right? You just went down the river. You could only generate 7 miles per hour with your little arms, and coming back, the river's going 5 miles per hour. So when you're coming back, the net is only 2 miles per hour, and it's going to take forever to get to 36 miles. All right. So that person should have taken my math class before he went on that little date. But anyways, number 8 says a worker invests $14,000 in two accounts. Now this problem was the same problem we did in chapter 1.2, somewhere around there. But we now have two variables and two equations. So a 2 by 2, two equations and two unknowns, which some cases makes it a little bit easier than just having one. But the problem is actually the same. We're just going to use a system on this problem. So let's start off by saying this person has $14,000 total, which is not a bad amount to invest. And they're going to invest some of it at 6%, and some of it goes at 11%. And you might say, why don't you just put all 11? Well, because 11%, usually the higher yield ones are more risky and you could lose more too. So anyways, you know how that goes. So if he received a total of $1,040 in interest at the end of the year, how much did he invest at 6%? Well, we got to know how interest works, right? And this is just simple interest. But if you had, let's say, $100 in this account, how much simple interest did you make after a year? Well, it's just going to be 0.06, right? 6% times 100, which means the amount of interest would just be what? $6 is the amount that's made that year. So we got to be able to know. We got to know how to do that to do this problem. Let me get rid of that, because we don't know how much is invested over here. So if we don't know something, we're going to call that an X. Let X equal dollars invested at what percent? At 6%. And then let's let Y equal dollars invested at the other one, 11%. Well, this gives us the flexibility that we need here. The first equation that's really easy to figure out is, oops, that wasn't supposed to happen. Oh, that wasn't supposed to happen either. The total dollars invested in this account is X, plus the total dollars invested in this account is Y, and our total dollars that we have started with was 14,000. So, you know, the amount in this account plus the amount in this account has to be the total dollars we started with. So that's a pretty easy equation. The harder one is writing the equation for the interest gained. Now we know that our interest is just going to be percent times the amount in that account. This percent is 0.06 times the amount X. This guy in this account is the percent is 11%, 0.11, times the amount in that account Y. And how much interest did they make in a year? Well, they're saying that they're going to make $1,040 of interest in that year. So that has to be $1,040 is the interest. So there we go. There's our system of equation. I think probably what a lot of people try to do with these things, because they don't like decimals, and that's optional. But what they'll do is they'll multiply, by 100, because they want to move two decimal places. So this is purely optional. Some people think it's super necessary, but it's not. It's optional. I'm going to take this one and put it right up here. And when I do that, let's see, space-wise, is this going to work out? Yeah, I think so. So when I do that, I end up with basically just moving the decimal point over to the right on each one. So this becomes 6x, and this becomes 11y. And this, be careful, move the decimal to the right, becomes 1040, and then two more zeros. So 104,000. Now let's go ahead and take this guy right here and write it up here. But I would like to set it up to have something eliminate. Let's eliminate the x's. That means multiply by -6 on the left and the right. Well, -6 times x is -6x, perfect. -6 times y is -6y, that'll work. And -6 right here times 14,000 gives us, what is that? -6 Negative 6 times 14,000 is negative 84,000. Okay, now let's go ahead and add those two up. And this is, we expect to happen right here, right? Is this negative 6 and positive 6x zero out. And 11 plus a negative 6 gives us 5y. And negative 84,000 plus 104,000 is just 20,000. And divide by 5. And y equals 4,000. Now we got to be careful. That's why we defined our variables. Y is the dollars invested at 11%, and they want to know what's invested at 6%. So I got to keep on going to get what x is, because x is dollars invested at 6%. So I got to figure out x. Y is not going to cut it. I can just go back to this original problem in black here that just says x plus y must equal 14,000. And once again, I could use my substitution. If you believe y equals 4,000, we'll then replace it right there. And so we got x plus 4,000 equals 14,000. Subtract 4,000 on both sides and you get 10,000. They were asking for what is invested at 6%. And you can see x is that value, so $10,000 must have been invested. Whoops, this thing's frozen all of a sudden. There we go. So $10,000 is invested at 6%. And that allows us to move on to the last word problem. And the last word problem is a mixture problem. This is our third mixture problem. See, so you can see that I'm trying to give you some practice with mixture problems. This mixture problem, instead of using the cat crap example with coffee, cat crap coffee, I want to use another example because with mixture problems, often they're mixing alcohol or acid. In this case, they're mixing titanium in alloy. An alloy is just a metal that's mixed with other metals, right? So they're mixing titanium in here. But there's something we kind of have to get straight when we're doing this. And that is when you're mixing something. So first thing I want to show you, so I'm just drawing a nice little small 2-gallon container. There's a 2-gallon container, and it has 95%. Let's keep it. Instead of alcohol, let's make it 95% apple juice. Okay, 95% apple juice. How's that? 95% apple juice. Now this other one is one of these big 50-gallon containers. You know what I'm talking about? They call them 50-gallon drums, actually. They're so big. 50-gallon drum, and this 50-gallon drum is 3% apple juice. Question I have is, which container has more apple juice? You see how this is the confusing part with mixture problems. Because you can first compare, well, this has 2 gallons of that stuff, and this has 50, so 50 is more than 2. But wait a minute, this container is 95% apple juice, and this is only 3% apple juice. So we got a real problem. It's hard to tell which one has more apple juice. And so the clue or the key to this is figuring out its purity, is the way some books call it. How much pure apple juice is in each container? And you can figure that out by multiplying the percent times the amount. That is a key thing to remember when you're talking about mixture problems. So I really want to know which container has more apple juice, the 95% apple juice at 2 gallons or the 3% apple juice at 50 gallons. So we can go like this and work it out. Our formula says take the percent times the amount. So the percent here is 0.95 times the amount, 2 gallons. And 0.95 times 2 is 1.9. So we got 1.9 gallons of pure apple juice. How about over here on this one? Well, this is 0.03, because we got to change 3% to a decimal. That gets multiplied by 50 gallons. And when we multiply this, we end up getting 1.5 gallons. So it turns out that the smaller container has more apple juice in it, pure apple juice, because it's 95%, and so 95. So you saw the purity. Okay, so this number right here is what's needed for when you're comparing things with mixture problems. Okay, this idea. So let's read this one out. It says a metallurgist, okay, a person who melts down metal and makes alloy, has an alloy with 10% titanium and an alloy with 30% titanium. So they've got this chunk of metal that has 10% titanium in it and another chunk of metal that has 30% titanium in it. He needs 100 grams of an alloy with 24% titanium. So, as I said, I'm kind of boring with the same old beakers. I guess it should be like a chunk of metal. But this is going to be melted down metal. Let's say it's melted down. And in this big pot, or what do they call it when you're melting? What is it called? I can't think of it now. But anyways, you get this big pot of melted down alloy. And we've got another one. What's the difference between them? Well, one of them has 10% titanium, the other one has 30% titanium. So there's the big difference. This one's 10% titanium, this one's 30% titanium. And what do we want? We want this new alloy. Of course, it's still going to be in liquid form because we make it super, super hot. We mix it together and then we cool it. You pour it into some mold and make something cool out of it, right? But what we want, he needs 10 grams at 24% purity. So it needs 10, no, did I say 10? Wasn't it 100? He needs 100 grams at 24% purity. Got to double check that, 24, okay. All right, the question is we don't know, and like I said, the question usually is going to be a variable. And the question is, how many grams of alloy are needed at 10% titanium? How many grams of alloy are needed at 30% titanium? There's your variables. Let x equal the amount of titanium at 10%. And then let y equal the amount of titanium at 30%. Okay, so x is the amount of titanium at 10% and y is the amount of titanium at 30%. So the hard equation is the one where you have to figure out what is the purity of titanium in this container? And that's just going to be percent. Remember my little equation? Percent times the amount. So that's going to be percent, like 0.1, if you want 0, times x, plus the percent of the next container, which is 0.30 or just 0.3 times y, equals, and then this one's going to be 0.24 times 100. And we know that just moves the decimal to the right, so 2 places, so it's 24. So there's our first equation. So now what we want to do is we want to take a look at our second equation. Now our second equation is the easy equation, because the second equation is just basically adding up x grams from this container plus y grams from this container better equal total grams. And so that's a much easier equation. That's just going to be x plus y equals 100. Okay, so now what do we need to do? We need to solve either by substitution or by addition elimination. Let's go ahead and take that little step that everybody seems to love, and that is multiplying both sides by, you could do it by 100, but then, okay, let me go back. I hope everybody realizes that 0.10 is the same as 0.1, and 0.30 is the same as 0.3, right? 1/10, which is like 1 dime, is the same as 10 cents, which is 0.10. Anyhow, I say that now because I don't want to move the decimal more than I need to. So I'm just going to multiply by 10 because that will move a decimal to the right once. This new equation is just going to be 1x, right? Then it's going to be plus 3y from this, and then equals 24 times 10, which is 240. So our next step is I would like to do something that eliminates something. And I can see that's going to happen as long as I multiply this x times -1. So I must multiply everything on the left by -1 and every term on the right by -1. And when I do that, I get -1 times x is -x, and -1 times y is -y, and 100 times -1 is -100. And then we go ahead and add them up. Of course, this zeroes out. Awesome. And then we've got 3y minus 1y is 2y. And then we've got 240 minus 100, which is 140. Divide by 2, and y equals 70. They wanted to know both, but remember what y was, just so we can interpret what I just did. Let y equal the amount at 30%. So we know how much we need at 30%. We need 70 grams at 30% as a little side note for ourselves. Well, how do you get x? Easy. Look at this equation right here. X plus y equals 100. Replace, once again, replace. Replace if y equals 70, well then we can just replace y with 70. And now we've got x plus 70 equals 100. And if I subtract 70 on both sides, I get 30. And remember x, when we go up here, x is the amount of titanium at 10%. So this is grams at 10%. Let's answer the question. Go back up here. We're going to need, now I forgot, 30 grams at 10% and 70 grams at 30%. And if you mix 30 grams at 10% and 70 grams at 70 grams at 30%, you will get 100 grams at exactly 24% when it's mixed together. All right, I hope this helped. And this is Mr. Gonzalez or Professor Gonzalez signing out. I hope you're having a great day. Take care. Bye.